If support search feels useless, the problem is often the ranking model, not the agents. We will build a tiny query likelihood search over tickets in Python, so similar cases finally show up when you need them. You open tickets and type a query, but results feel random. In this video, you will learn a simple language model ranking you can implement quickly and reason about. By the end, you will understand how smoothing, collection stats, and a small metadata filter change what rises to the top. I'm Professor Pi, teaching search and IR from basics to advanced with simple, concepts-first Python that helps you solve bigger, real-world problems. Support ticket search is about surfacing past cases that help resolve a new incident. Teams reach for query likelihood when they want a principled, textual ranking that treats each ticket as a little language model. It is lightweight. It scales from a handful of tickets to thousands without turning into a black box. At a high level, query likelihood asks this question. Given an agent query, how probable is that query if it was written by each ticket? We score tickets by that probability and rank. Smoothing prevents zero scores for unseen words and lets the model generalize from the whole corpus. We will build a tiny corpus, score a single ticket, rank the whole set, add a metadata filter, and then swap to a stronger smoothing model with collection frequencies. Each step stays small and interpretable. That keeps the math friendly and the results inspectable. This snippet builds a tiny ticket corpus and a clean tokenizer. We store 4 short tickets in the dictionary docs, where keys are IDs like T1 and values are texts. The function talk, lowercases, and keeps only letters and numbers, giving us predictable tokens for scoring later. The set comprehension over docs collects unique words into vocab, which acts as our language model's dictionary. A compact corpus like this makes the math easy to reason about, yet keeps realistic support terms like VPN and password. The printed counts confirm our starting point and the vocabulary size the model will work. Now, we will score 1 ticket against an example agent query. This snippet scores 1 ticket under a Laplace query likelihood model. We build TF with counter to get word counts per ticket, then set Q as the agent's query. For ticket T1, we compute Z as its length plus vocab size, the denominator for Laplace smoothing. The variable S sums log probabilities of each query word given T1, using +1 to prevent zero probabilities for unseen words like connect. More negative means less likely under this document's language model. The printed score shows how compatible T1's wording is with the query. Next, we will rank every ticket and return the top matches. This snippet ranks all tickets by query likelihood with tie breaking. We pre-compute Z for every ticket, then build SC as a dictionary of log scores for each ID under the same Laplace model. The sorted call orders IDs by descending score and uses the ID itself as a stable secondary key to break ties deterministically. Slicing to the top 3 keeps results compact and focused, like a ticket list in a help desk UI. The printed list shows the most relevant IDs for the query and highlights the best candidate. Now add a practical routing step so we only compare similar queues. This snippet adds a simple metadata filter before ranking. The dictionary meta attaches 2 fields per ticket, a short OS label and a team label. We keep only network tickets as candidates, which mimics routing queries to the right queue before scoring text. The same Laplace score and Z values then rank the smaller set, saving time and pushing obviously irrelevant queues aside. If your filter is broader, you'll get more candidates. If it's narrower, results get faster, but risk missing options. The printed list shows the top network tickets only. Next, we will replace Laplace with Dirichlet smoothing and use collection counts. This snippet upgrades to Dirichlet smoothing plus a pragmatic OS filter. We build CF as collection counts and TOT as total tokens to estimate collection probabilities. Then set mu to control smoothing strength. The query queue targets VPN sleep, so tickets that mention sleep get boosted by observed counts, while others back off to the collection. We rank only Windows or Mac tickets to match the agent's platform needs, then sort deterministically. Increasing mu leans more on collection frequencies, safer, flatter. Decreasing it trusts document counts more, sharper, riskier. The printed list shows this tiny toy maps to a real help desk workflow easily. Replace the 4-ticket corpus with your ticket store. Keep the tokenizer consistent, and run the same scoring for live agent queries. The metadata filter becomes your queue router, and smoothing settings carry over when you index more tickets. The principle stays the same, and the scores remain inspectable. Recap: query likelihood treats each ticket as a language model and ranks by how likely the query would be generated by that ticket. Use it when you want a transparent, text-first ranking and simple tuning. Caveat: it relies on surface wording and smoothing choices, so it can miss semantic matches without extra features. Next step: tune the Dirichlet mu parameter and measure how precision and recall change when you scale from a handful of tickets to thousands. If short, practical IR helps, subscribe and watch the IR videos.